Okay, good morning, everybody. Let me start by thanking very warmly the people who are responsible for me being here. Claudine, Gertrude, Catherine, Pasquale, Sergio, and Sébastien. So it's my first time to Brazil, actually, and I'm enjoying it a lot, as you can see here. I'm also learning a lot about why hidden order has not yet been found, and some kind of emergent phenomena where you don't expect them. Okay, but now I want to come back to first principles calculations. So my name is Silke Biermann. I'm from the Centre de Physique Théorique in Palaiseau, and if you're wondering where Palaiseau is located, this is just a few kilometers south of Paris on this campus here of École Polytechnique, where you have a building where you have strange people here treating electronic structure, and in particular, first principles calculations for correlated electron materials. So we try to, as much as possible, to avoid adjustable parameters and to do calculations for materials which are particularly interesting, but also sometimes particularly challenging. So what does it mean? The plan somehow is that we want to address not only ground state properties, but also spectral properties of materials with strong electronic Coulomb interactions. That means materials we need to go beyond the single particle picture, beyond static effective potentials. We want to do so at finite temperatures, but as I said, we want to do so as much as possible, avoiding introduce adjustable parameters. And the strategy here is to combine techniques from many-body theory and from electronic structure theories. So now when I say many-body theory here in this talk, this will actually be a big name for essentially in-field theory and extensions. In practice, in daily life, we work a lot on what first principles electronic structure theory should mean here. Should it mean just density functional theory, or can we do more refined interfacing, for example, based on many-body perturbation theory schemes, directly working with Green's functions and so on, how to calculate actually the effective interactions that you need to correct these electronic structure theories. And that's a big topic in our lab, but I will not talk about it. I'm just saying that if anybody's interested, for coffee discussions. I will equally well, for coffee discussions, flash 3 slides on other systems than Iridates, oxides, F-electron systems that we're interested in, and then I will come to the main topic, as Ricardo announced, like Iridates. So the first example here is classical oxide, vanadium dioxide, with a metal insulator transition. Here, conductivity as a function of inverse temperature, jumping by several orders of magnitude. And this has been looked at in photoemission here for the metallic phase, the insulating phase, and it's nicely captured by the kind of methods we are developing. Second example, metal, little brother of the iron nictide. So here, barium cobalt 2, arsenic 2. A nice introduction to the nictides today. This is the result of the calculation compared to photoemission. So the bluish, greenish, brownish stuff here is actually experiment, and we have superimposed here in these black, red colored lines the results of our calculated spectral function. So now this may not look spectacular, but if the initial comparison of just the DFT LDA band structure compared to experiment, then we are quite happy with that. And the last appetizer example is actually a simple system, a mod insulator, a cerium fluorosulfide compound that you can actually use because of the nice red color here to color your smart or something else. The band structure calculation, the fact that it's a 4F1 system without symmetry breaking, without magnetism, already tells you that any band theory will just pile up the cerium 4F at the Fermi level and give you nice metal, which, of course, if you look at this, is not what you expect to find. So what you want to see is actually that this is an insulator with a gap of about 2 eV. And so this was our last example here, where we need to take into account, at least as a minimal model, the local interaction on the cerium 4F shell in order to localize the cerium 4F electrons and then open up a gap here corresponding to the color of the compound. Okay, with these appetizers, if anybody's interested for coffee, I come to the the real topic of my talk. So I want to focus on strontium-2 iridium-04 and related compounds. I will give you a basic introduction to the electronic structure of that, make some methodological remarks how we actually go about for the calculations, and then I will focus in particular on one aspect that we have been excited about quite recently, namely the role of non-local correlations in order to really obtain a nice description of this compound in comparison to angle-resolved photoemission. And this also gives us a kind of interesting scenario for some things which have been claimed to be quite exotic in the experimental literature, in particular here this notion of the pseudo-gap. Okay, so strontium iridate is actually more or less isostructural to the celebrated lanthanum cuprate here in this kind of double kite structure, from which it is distorted though by a rotation of the oxygen octahedra of 11 degrees around the c-axis, and that gives you a unit cell with 4 iridium atoms. Disclaimer, I will disregard possible additional lowerings of the symmetry from the resulting I41ACD and just use that structure. ARPIS optics transport have consistently characterized this as an insulating compound. Here the ARPIS spectrum, the optical gap, even though strongly dependent on temperature, persists at high temperatures, in particular above the magnetic transition, and resistivity going as an insulating compound. Now the fact that duration is a 5d5 filling already tells you that this cannot just be a simple band insulator, at least not in the paramagnetic phase. So I refer to paramagnetic phase because we have a magnetic transition at 240 Kelvin from a candid antiferromagnetic phase here to the paramagnetic phase, and our focus in the following will indeed be on that part, because precisely there it is clear that you cannot get it in a band picture at all. Okay, usually when you think about correlated materials, you think about 3D materials, because you have orbitals living to the nucleus, electrons seeing each other very strongly, and it's only over the last 10 years people have realized that going from 4D to 5D can still be interesting, despite of the fact that the radial wave function here, 3D, 4D, 5D, becomes more extended, can have additional catches, and this has been nicely explained by the talk by if you have, in addition, spin-orbit coupling. So spin-orbit coupling, of course, increases when you go down here. And then in the iridium, this has been discussed in detail, so I can go through quickly. You have a splitting of the 5D shell here, first into EG and T2G by the crystal field, but the T2Gs are split again into what it is common to call J effective 1/2 and J effective 3/2 in an atomic picture. And then it has been realized quite exactly 10 years ago that strontium iridium-04 here might be a mod insulator, because actually it's just the lone 1/2 band that survives, and that is very narrow and then split by even moderate Coulomb interactions. Okay, since then the literature has exploded, and I apologize in advance for maybe missing whatever people in the audience have been doing. I just flash a few motivations still, in particular pointing out the possibility that this is akin to the cuprates, because isostructural structure, of course, and also because of the fact that you have one hole in this T2G. And this analogy has been pushed further here by pointing out that it should be described by some kind of twisted single orbital Hubbard model for the 1D compound, for the one orbital compound. Then experiments were searching for analogies, and here it was claimed that there are Fermi arcs coming up when you manage to surface potassium dope the thing. On electron doping, hole doping has here completed these Fermi arcs to rather have ellipses, but still with interesting features, where here this group analyzed somehow the behavior of the spectral function and identified that what they called a pseudo-gap. Okay, superconductivity in a direct probe has not been found, but people are trying and wanting it. So if yeah, if you want to join this race. Okay, as I said, I focus on the temperature phase here, and we are going to try to get the spectral properties from first principles. And that means, in a nutshell, using DMFT, using dynamical mean field theory, as explained by Maria Gardner, in conjunction with density functional theory here. So that means, in a cartoon picture, we map our solid on an effective atom where we keep local effective Coulomb interaction, how about you? And the environment of that effective atom is mimicked by an effective bath, which replaces, so to say, the environment of the atom. So the environment can give electrons to the site or can take electrons from the site. So locally, we could have fluctuations here where electrons hop to the side, go away. So you can have local quantum fluctuations governed by the effective local Hubbard interaction. And then the bath had to be determined self-consistently in order to re-rate it back to the solid that you have. Okay, so now we want to do so without introducing parameters. And for that, we use here in this work density functional theory. This theory originally has not been designed for that purpose, but initially it gives you a mapping of an interacting electron gas onto a set of non-interacting electrons, put in an effective potential, which is determined in such a way that the ground densities of the initial system and the effective system are the same. So now we don't use this theory to calculate ground state properties, but we abuse it, so to say, in order to generate the parameters of a single particle Hamiltonian, hopping, level positions, and so on. So that means we arrive at something which more really looks like a multi-orbital generalization of a Hubbard Hamiltonian, where we have single particle terms coming from the FT, and then we supplement that explicit Hubbard or Hubbard and Hund's interactions here in a multi-orbital framework. Okay, I'll skip that and directly to the now DFT first results for strontium Iridate. So if we do the band structure calculation just from DFT compound, you find roughly here the set of T2G states, the EG states pushed up. Here you have oxygens coming in. And this is just a color choice which has no deeper meaning to point out that at the LDA level, indeed, you have something like a set of bands showing up here at the Fermi level and some a little bit further down. Note that because of the 4 iridiums in the unit cell, a single band means that we actually have 4 bands, and this is what you see here at the Fermi level. Yes, this doesn't mean that this is exactly the J effective 1/2 character. We can analyze where the J effective 1/2 character is in fact sitting, and this has been done here. So this is now a projection of that band structure on local orbitals of the pure J effective 1/2 or pure J effective 3/2 characters. This is for the 1/2, this is the 3/2. There you see that indeed the character is roughly where this color coding was suggesting it, even though things become a bit more subtle. In particular, this branch here is in fact a 3/2 reaching up to the Fermi level at the LDA. So that also in particular means that at the LDA level, this compound is not polarized in the sense that you really have, that you really have one hole in the J effective 1/2 state, but you have some mixture where there's more charge or more hole actually in the J effective 1/2 than in the others. Okay, so let's look at the numbers. If we look at how much charge is actually in the respective 1U orbitals, then we find that, okay, for the 1/2 and the 3/2 here, these are close to 2, but not quite. This is close to 1, but not quite. However, now we branch our machinery, we do DMFT on top of that DFT Hamiltonian. So now we add Hubbard interactions, we solve that problem, we look how the charge redistributes, and the first thing that happens is indeed to clean up and have this remaining part of the hole go here. So now we have 1, 2, 2. So now we really have a J effective 1/2 state, but this is already the effect of putting correlations. So for that reason, we call this here reduction of the effective orbital degeneracy, because in principle you start from a T2G model, and only once you add correlations, you go to a single orbital J effective 1/2 state. Okay, so now let's analyze the result for the spectra for that J1/2 state and the others also. So this is the spectral function. Here in the color plot, we plot the total spectral function, from which see already that at 0 we have opened up a gap. Spectral weight has maxima here at these features, and there is some faint stuff here, which is the one hole. So you have a ratio of intensity of 1 to 5 because of the filling. Now you can divide into effective 1/2 and the J effective 3/2 contributions. And as this effective 3/2 does not have anything in the unoccupied part anymore because it is completely filled, so we stop here. This is the spectral features for the 3/2. And the 1/2 is now half-filled with a gap opening here at the Fermi level. So we have managed to reproduce, even in the paramagnetic phase, the opening of the gap, the insulating phase, and we have now complete orbital or spin orbital polarization. Okay, how comes? So you start off with 3 orbital model, and now you add the interaction and you get insulating. Well, we have already one clue, namely the fact that it becomes single orbital helps, because a single orbital model is much more easy to drive insulating, even with moderate interactions, than a 3-fold degenerate one. That is very well known in a model context. But you might get nervous because there's other compounds around. In particular, the little brother, strontium rhodate. Same story from the structure point of view, filling point of view. It's just a 4D compound. And interestingly, this thing is actually metallic. So once we got the iridium, we got a bit nervous when we were thinking about this. But then we started the calculations, first at the DFT level, the comparison between the rhodium and the iridium. Interestingly, the band structure is even a bit more narrow here than in the iridium. The spin-orbit coupling is a bit smaller, roughly half of that. And also, interestingly, the Hubbard U is slightly smaller, which might seem counterintuitive at first sight, because it's a 4D compound. But you can rationalize that by the distance to the oxygen states, which actually do screen more efficiently here in the rhodium compound. So if you have a T2G model in mind, you should take the screening of the oxygen states, which is efficient, and reduces actually the Hubbard U. Okay, so let's do the calculation for that compound. And now again, the spectral function, here the total one, and the orbital resolved ones, J effective 1/2, 3/2 here. And what you see is, in fact, nicely, the metallic character is preserved. There is a reduction of effective degeneracy, but only in the sense that one of these orbitals goes down, the other one stays at the Fermi level. So you can say that effectively you go from a 3-orbital model to a 2-orbital model, plus a filled state. So these quantitative differences, new spin orbit, lead actually to a qualitative difference in the properties that is captured here in the calculation. You can push this further and compare to ARPIS. I will go quickly, just show you the Fermi surface here. So this is the calculated Fermi surface, and this is the measurement from the group of Felix Baumberger. If you compare this here, it looks very nice. If you compare it with the original DFT Fermi surface, this does actually not work so well. And precisely because of the fact that one band has sunk below the Fermi level, and that is in fact happening also in nature. Okay, so now we are quiet about the fact that our technique finds the difference between the iridium and the rhodium, tracing it back to these subtle differences in the input. But let's get back to the spectra of the iridium compound. So this is what I've shown you before. Here, the J effective 1/2, 3/2 spectral functions. And now let's compare to photoemission. So photoemission is here and here, actually in the first and in the second Brillouin zone. So in the theory, of course, we do not have a difference of first and second Brillouin zone. So that means that this is actually due to matrix elements effects that go beyond what we calculate. We just calculate the spectral function and not the matrix elements. So what we are arguing here is that you should roughly take the sum of this and this in order to identify the features from the theory. Because in experiment, in one Brillouin zone, you see more, and in the next Brillouin zone, you see the remaining ones. This doesn't say anything about the weights, but at least it tells you roughly that you should see features here, here, and here. So now, here's the calculated total spectral function. And what we see is that actually these features here fit very nicely. This is the 3/2 features. However, if we look at what you would get, or what you would expect in the theory from the 1/2, you would expect something very flat, non-dispersive, weakly seen here actually, which does not correspond at all to what we have here. On the contrast, the J-effective 1/2 band here is strongly dispersive and has, well, little in common with that theoretical feature. So this looked very depressing at the first sight, but then we were working a bit, we were working a bit harder. Namely, we were including non-local effects. So I told you in DMFT we have an effective atom, so our many-body self-energy is a purely local, atom-centered local many-body self-energy. And what we do now is to inter-iridium fluctuations in the form of an inter-site self-energy. We do so on a very crude and simple level by just taking a dimer of iridium atoms and using that as the atom that we treat in the DMFT. If we do so, we get a modified calculated spectral function here, and the first thing you immediately see that in fact that introduces the very strong dispersion of the J-effective 1/2 band that you see in the experiment. So indeed, this feature here is a clear signature of these intra-dimer, inter-iridium fluctuations. So now, we take a dimer because we want to have the minimal model. This is not a statement about the range of these fluctuations. It's just saying that in order to capture the spectral features, this is the minimal model. We also do further simplifications. We didn't recalculate the 3/2 states, and we used the cluster Hubbard 1 approximation for the 1/2 state. Even that is actually enough to just capture these features. Okay, let's compare a little bit more. So from the experiment, we also have cuts. This is experiment here and here at different constant energies. So we are here and here, so to say. And also there you can see, okay, theory, experiment, this fits very nicely. So we believe that actually this dimer correction uses the necessary non-local effects that you need in order to get a good description. Okay, based on that, we now get crazy. We go to the doped case. So we put now 10% electron. So the thing becomes metallic, as you see here now, immediately. And also there, we have photoemission data. And in particular, from experiment, it was pointed out that around the M point here, you have a very steep, well, waterfall-like feature, whatever you might want to call it. Actually, the blue dots that you see very faintly is actually extracted from the ARPAS, and that is corresponding here to these features here. So, the doped case, this seems to be working not so badly. But let's get back to the Fermi surface. So let's see here. So we have introduced by the doping a Fermi surface cut around the endpoint. So we are getting a pocket. So let's plot the Fermi surface. Here around the endpoint, we have a pocket which has this elliptical shape. And this is... So now, in ARPAS, people were arguing that running around on these contours here, you were actually detecting a pseudo-gap. So this was from the paper of Felix Baumberger. Starting at some angles here, they were measuring that there was some kind of depletion at the Fermi level. So we do the same procedure from our theory data. We symmetrize the spectral function. That means particle-hole average, as experimentalists like to do it. And we identify some regions here of some kind of gap. How comes? Well, I have a little bit more on the methodological point of view. I told you we have a dimer self-energy, but you can put a dimer in different ways. So if you just dimer, you break the symmetry of the system. This is not what we want to do. In the philosophy of T, that calculates a self-energy and then implements a self-consistency condition in such a way that the symmetries of the original problem are restored, we actually put up a cluster DMFT scheme, which we called oriented cluster DMFT, where we put a self-energy for the dimer, but then do an averaging in a way that the symmetry of the system is restored. It means we not only over K here to get a low for the experts, but also over the symmetry operations of the point group. That means here the two dimer orientations. So that means that we actually have a dimer in that direction, a dimer in that direction, and the effect of putting a self-energy in a given direction is to slightly modify the hopping, and that means tilt slightly the ellipse out of the axis. Averaging now means that we have actually two ellipses out of the axis, which once you have lifetime effects experimental resolution, you will never resolve, but at the borders here, the corners, you will see some kind of depletion. So we believe that this is actually what is more or less happening here when experimentalists analyze the data. However, there's a second catch, and this is the symmetrization, because look at the spectral function here. In particular, at the x point, this is not just this band crossing the Fermi level and nothing happening. There is the lower part of the band here coming up, very close to the Fermi level, and when you average, you will actually pick up spectral rate of that band, pretending that you have a pseudo gap. But that just means that actually you should not do the particle hole symmetrization. Okay, my chairman is standing. Sorry? Good. So I let you read my conclusions. I will not show you about them. Thanks a lot.